Okay, so we'll start the session now. So my apologies about having this session on a different day. So our general meeting day is Tuesday, but because I had some things on the last Tuesday I had to meet today. So not expecting too much of attendance today, but yeah, we'll anyway talk about this week session. Yeah. Okay. So last weeks we have read and learned some of the handcrafted features that used to be there before the deep learning era. So how people used to handcraft features given images and learn a representation of the image and use those representations for different tasks. Then we saw neural networks coming up, uh, where this handcrafting of features was automated. So basically the task of the network was to learn the features itself and then learn how to use those features to perform some downstream tasks. So we have gone through CNNs already, and the visualization part of CNNs, the different CNN architectures and so on. And now we'll look at some applications of CNNs or these neural networks. So it's not enough to just use these neural networks as it is, right? So they must be of some use. So that is what we are after. So what downstream tasks can these models be utilized? So all of us have seen image classification, but in this particular week we have focused on things like object detection, object segmentation, and so on. So this TA session is like a revision and overview of the same thing. So I'll just quickly share my screen. Yeah, okay. So, like I said, today's class will be based on how to detect objects in a given image, how to like localize objects, and so on. And so, we'll first start with some fundamental understandings. So we use different terminologies in deep learning and the machine learning field, like classification, localization. Just a second. Yeah. So we use different terminologies like classification, localization, detection, segmentation, and so on. And each of these have some differences with each other, right? So the first thing is to understand what these different terms actually mean. So this is a very famous slide which has been used by Sir, as well as it is generally used internationally as well, just to explain what these individual tasks mean. So the first task is classification, where given an image and an object in the image, all the model needs to do is just to say that okay, this image has a cat in it, right? It has to just classify that it has a cat in there's a cat in the image, right? So that is what is known as classification. When you add this term localization means that I'll classify this object to be that of a cat, and I'll also like localize, right? I'll draw a bounding box around this object, and I'll basically show that in the image where the cat is present, right? So that is what is known as localization, this task of drawing a bounding box around the object. Third is object detection. So object detection is exactly what? So suppose in an image, generally when we take an image, it doesn't really always have just one object like this, right? So the images we see around us, if you look around yourself, maybe it will be something close to this, where there are multiple objects, multiple different kinds of objects, like, right? So maybe on your desk there's your laptop, there's a copy, there's a pen, and so on. Maybe there are 3 pens and so on. So that is what is object detection. So you need to detect each of these individual objects and also multiple instances of them, right? So for example, in this image you can see one dog. So that is represented by this blue box. Then this duck, green box, and there are 2 cats. So these are given by 2 boxes. So each instance of each object has to be captured. And first of all, there are 2 tasks. I mean, in object detection there are 2 tasks. One is that the object you have captured, you need to classify them, right? So for example, here we find that this red colored box belongs to a cat, this blue colored box belongs to a dog, and this part belongs to a duck. So we classify the objects first of all, and around the objects we have drawn boxes, right? So object detection is nothing but classification and localization meant for multiple objects. So this is for a single object, this is for multiple objects. So this is what is object detection. And finally we come to instance segmentation. So instance segmentation does what? It basically, it goes to the image and it does a pixel level labeling, right? So it will, wherever this dog, in whichever pixels this dog is present, it will label those pixels as those of the dog, right? So here, like, you are drawing a bounding box. So here you are just like drawing this box around the dog, and there's a lot of space here which do not actually belong to the dog, but you had to draw this box in this way because this is how you draw boxes. So instance segmentation is a little bit more involved task, where instead of drawing a box around which will capture many other pixels, I'll point out exactly which pixels belong to the dog, which pixels belong to the cat, and which pixels belong to the duck. So these two are meant for multiple objects, like it's written here. These two are meant for multiple objects, and this is for a single object, right? So that is what is these are the tasks that we want to look at in this particular session. So we have already looked at classification, but how to do localization or object detection, that is the main agenda that we have for this particular session, right? And also we have gone through in this week's lectures, we have also gone through instance segmentation, but we will not be focusing too much on it for this session. Maybe we will go through some code, right? So first of all, before so now we all have an idea that all these tasks are basically performed by different neural networks, right? So how those neural networks are designed, etc., that we will go through, that we have already seen in this week's lectures already. However, all these tasks, they used to be there even in the pre-deep era, right? So before deep learning came and became popular, all these things were already there. So there were different algorithms for it, and one such algorithm was the Viola-Jones algorithm. So wherever you go about learning, wherever you want to learn object detection, you always begin with this algorithm, because this is where you do not learn the features, but these were like not handcrafted, but these were like specific features used to detect objects. So you should already know about it, right? So, and you will also find that the Viola-Jones algorithm and other algorithms which were released in the pre-deep learning era, they involved a lot of math and lot of intuition, because this single algorithm, without even having to look at many data, like I keep saying, so without having to look at billions and billions of images, these algorithms that people prepared at that time, created at that time, they would work for many of the images, right? So the Viola-Jones algorithm is such an algorithm which doesn't involve any deep learning, right? It has 3 steps. So the first step uses hard-like features and integral image technique to speed up computation, right? So this integral image technique, so we will go through it in a bit, but yeah, you can see the first thing, that there are some hard-like features, means there are some specific filters, right? Like Gaussian filter is a specific filter, Sobel filter, and all those things that we went through in the beginning of the beginning of the course. So similarly, hard-like features are filters which are designed specifically for some purpose, right? So this is where we would like to point out that normally, had it been deep learning, these features would have been learned, right? But here, because we are not learning anything, we are predefining these filters which we want to convolve with the image, and we want to find out certain characteristics of the image, right? So basically the moral of this story is that you use these HUD-like features. So just imagine there are some kind of filters that are good at, you know, detecting like different objects, right? And so this whole algorithm is standing on top of using these features to detect these objects in the images. And then just to make this process very fast, so we'll go through this. So integral image technique, which sir has already explained, so that is being used in order to make this process very fast. So then basically, so for every feature that we see, every feature, every filter that we create, we'll create a weak classifier based on that filter's output. And these different classifiers, they are basically weak classifiers because they are basically dependent on each of these weak classifiers are dependent on a single feature. So these weak classifiers will combine using the adder boost learning, right? So that is the second step of the Weiler-Jones algorithm. And third is that we are trying to create a cascade of classifiers because we want to, like, for example, it may very often happen that you have a lot of since these convolution steps, they happen like window wise, so many of the windows that you have convolved the features with, they do not contain any object or anything of interest at all. So to make the process even faster, this method of cascade of classifiers is used so that you go on rejecting the bad windows, the bad places in the image which do not contain any object or any interesting information. So these are the three steps that are involved in this Weiler-Jones algorithm. So HUD-like features are basically very simple features. They are something like this, that so like these filters, you can see they can be of different so they can be of different sizes, scales and so on, and so they can be like this. So there's a black area here and white area here. So these are very common to the edge filters that we used to have. So white here, black here, right? Similarly, these are different kind of some other category of filters that we see, right? So these are called the line features, and this checkerboard pattern is called the four rectangle features. The idea is what, that when I'll convert the image with, suppose, this filter, how I'll go about it is that I'll take a sum of the area under this white pixels, so some of the pixels which are falling under these white pixels, and I'll separately form sum up the pixels that are falling under these black pixels in the image, and then I'll take a difference of these two, right? So this is going to be the algorithm for all of these, right? So here in the checkerboard also, so we'll take the white ones, sum them up, and then we'll take the black ones, sum them up, and then we'll take a difference, right? So that is how we are trying to basically detect that if the difference is, suppose, a lot, that would indicate kind of that, yeah, something has happened here in this region. So for example, when you have this particular image, this image of a person, so here you can see that the eye area is a little bit darker, then the outside area is probably a little bit lighter and something like that. So now when I put this filter on top of this eye region basically, so what I'll find is that, again what I said, that when I'm convolving, my only job is just to get a sum of the pixels in this location, in the black location, and get a sum of the pixels of this white location in the original image, by the way. So you take these two sums and you find a difference. Now when you do that, you'll see that, okay, this difference, so because this black area, this eye area is a little bit black and the below area is a little bit white, that's why the difference between these two regions is going to be very high, right? Similarly here, so this area is a little bit whiter, this area is a little bit darker. So hence, if you have a filter like this, then these two, like we'll take a sum of this and this, so we'll join the black regions, and we'll take a sum of this white region separately, and we'll subtract the black from the white, or white from the black. So that will like tell us if so because this basically this is covering the eye region, here and here whatever value you are getting, there will be a lot of difference with this value, right? Hence your this will kind of tell us that okay, there's probably an object here, right? So this is how the algorithm used to work, right? So now what about the second step, integral image? So integral image is nothing but a way of making this thing very fast, right? So all you need to do at every point is so here, like you can see that what we need to do given a filter here is not exactly to multiply the, like what we generally do with convolution with CNN. Suppose that we take the we take the values in the kernels in the different filters, and we multiply them with the pixels in the image, and then we do a dot product basically. That is how we do, right? But here that is not required. All we need to do is we'll need to find in this black region what is the sum of the pixels in the image, and in this white region what is the sum of the pixels of the image, right? So this is how we want to convolve. So that's why this integral image trick they formulated, that here suppose this pixel value is 38. So when I now what I'll do is I'll do a dynamic programming trick, right? So how will I do it? So at every location, yeah, okay. Yeah, so what I want to do here is at every location what I'll do is, suppose I am here, this pixel value is 38, I am okay with that. When I am here, this pixel value is 66, but this is the original image grade. I'll have another grade, and here what I'll do is I'll store this 66 plus 38, I'll calculate this sum and I'll store it here, which is 104. Similarly, at this location I'll store the sum of this 38 plus 89, which is 127. Okay, and now when I want to calculate suppose at this location what I'm going to do, this location basically carries the sum of this entire 2 cross 2 cell, right? So this 38 plus 66 plus 97 plus 89, that is given in this location, correct? So in this way you find the at every location, basically you do the dynamic programming in such a way that at every location, suppose in this cell I'll have the sum of the pixels across this entire thing starting from the beginning. So this entire square that I am marking, so this entire square region sum will be there in this location, and that is given by this 1013. So I hope this is the same slide we have shared as sir had used for teaching. So I hope that you have verified that these values are correct. In fact they are, it's just for your understanding to see whether you get the whole concept or not, right? So at any location, like I said, it's basically from, if you take a rectangle from the beginning location to this location, the sum of the entire rectangle is given by this particular location in this in basically this this box, this grid. So that is how you create this grid. And now why do we need this grid at all? Because suppose if I now want so I want to perform Weiler-Jones here, so I have this particular filter, right? So what I said, I need to have a sum of this black location and a sum of this white location. So now suppose the black location corresponds to this, okay? So then what I need to do is, instead of going ahead and finding out the sum here, I can directly do it by sum. So this, you can see, this can be order of n square, right? If we assume that this is a square image, then this summation itself also is a order of n square task, because you do not know how big the filters are going to be. But if you do this integral image, then what will happen is, by using some formula which you can go back and look at, so all you have to do is you have to manipulate these scores a little bit. So you have to add this 1492 with this 532 and subtract this 798 from 1027. So then, so basically what you, if you look at these squares, so if I want, suppose this, the value of this this particular square that I am pointing, right? So all I need to do is I need to take the value here, add it with the value here, and subtract these two values, right? So that happens in this grid, but because the boxes are here, I explained it in this way. So at the end, just by using a few summations, right? So I have been very easily able to find out the sum of the pixels in a certain location. So I do not need to count them again and again, because this can be big O of n square complexity. And also this is, by the way, not the only filter that you have to pass your image through, right? So suppose your filter size is something like 20 cross 20. So you can have multiple combinations of these things in that, inside your filter, right? So it can be like this, it can be like this, all these 5 alongside these 5 other different filters might also be there. So there can be many filters, right? So every time if you need to given a filter, if you need to convolve it every time, it will take a lot of time. Hence this is just a shortcut way of doing it, which makes it very easy, right? So you only need to compute this summation matrix for once, and then given any location in the, if you want to have the sum of any like location or any rectangle inside the image, you know how to do it. So there is already a formula that is given in the lecture slides. So that makes the task very easy, and that makes it basically constant time instead of n square complexity, right? So this is how, so this step is all about these two steps basically, the hard-like features and the integral image. They basically tell you how to use, what are these features and how to use them, and how to use them very fast. So that covers these two steps. Now in the second step, what we do, so we had mentioned here that so each of these features that we have, right, we'll convolve them across the image, right? And what we'll do is, there's a formula again that is given in the slides, you can go through them in the lecture slides. So as we convolve this particular filter with different parts of the image, we'll have a classifier which will tell that, suppose given this particular filter, I mean once you have convolved this filter with the image at this particular location, based on the value that you get, you can, so there's a classifier which will tell whether there's an object in this location or not, right? So if you have suppose maybe like thousands of features like this, you have thousands of classifiers which will tell you, like given a particular feature or particular filter like this, whether whether a certain object is there at this location or not. So it's like having different classifiers for different filters. So you have thousands of suppose 1000 filters you have, then you will have 1000 weak classifiers, which only depend on the output of this particular filter in order to tell you whether there is an object in this image or not, right? So you have all these weak classifiers. So they are weak, why? Because they are just looking at one feature, right? So they are here, for example, it's looking at this kind of a feature. So it's looking at just one feature and then it's trying to make a decision. So that is why all of these classifiers that are associated with the individual features, they are all weak classifiers. So now what we do here is we use the adder boost algorithm, right? So in order to, so adder boost does what? So it basically combines multiple weak classifiers and it does a weighted sum of them to create a strong classifier. Some visualization is given here, but yeah, the advice would be to go back and have a revision of the algorithm here that is given here in the link. So basically, suppose you are given a data set and you have two weak classifiers like this, right? So the first classifier draws a decision boundary here, but it misclassifies this red point. Similarly, the second classifier draws a decision boundary here. It misclassifies this red point, and you can see that this red point is almost lying on the decision boundary, right? So now what adder boost is able to do is, it is able to combine these two classifiers into a strong one, such that now you are able to pinpoint, you are able to draw a decision boundary that's like this, right, where you can like isolate the green ones from the red ones. So that is what is the adder boost algorithm. So just understand it here in this way intuitively, that you have multiple features and one classifier attached to each feature. So now all you are trying to do is, if you like, for example, you should use all these filters in order to make a decision, right, whether there is an object present or not. So how to aggregate the information that you are getting out of these individual features, that is what they are doing through the adder boost algorithm, that I have so many classifiers attached to each of the features. Now I'll combine them into one and make a single decision, right? So that is the use of this second step. So that is why we use adder boost to combine different weak classifiers and convert it into a strong one, right? So now the third algorithm is something like this, that you have multiple stages, right? So these sub windows, basically they are like this. So suppose this is a sub window, right? So when you convolve this particular filter at multiple locations, right, most of the times you will not find any object at all, right? So for example, had this filter been towards the top, so that would have covered just the forehead, and just by looking at the pixels of the forehead you wouldn't know whether there is an object or not, right? So this window basically wouldn't account for anything if the filter had been here. So this would have been an unimportant sub window. So this step 3 is a cascading of classifiers, where what they do is they go on. So this sort of an algorithm is very common in the deep learning area also. So maybe not cascading, but other algorithms are there, like non-maximal suppression and things like that. So what they do is they take all the sub windows, and at each stage they basically look at the different like the weak classifiers, the outputs, and they go on rejecting some of the bad sub windows which are not required for, which do not have any object content, right? So how we do that exactly is not of too much concern to us, but just know this, that at every time step, so at every step what they are doing is they are going on dropping some of the sub windows which are unimportant for detection of objects. So at this stage I am dropping some. That means that that in the second stage I am carrying forward fewer sub windows. So now based on some other criteria, I'll drop some other some of the remaining sub windows. So in this step I have even lesser number of sub windows to look at to find out whether there is an object or not. So this we continue for some time steps until we are satisfied with the result. So that is what is cascading of classifiers, which is given here, right? So this basically makes sure that you are rejecting the faceless sub windows very quickly, right? So that at every step you have lesser and lesser windows to look at, because with so many filters and so many such big images, so this image may be a like a 1024 cross 1024 image, right? So imagine if there are many such features, many such filters, how many sub windows you are going to get, right? So and most of the times the one common thing in object detection is that most of the pixels in the image, they do not convey anything, right? So suppose in this cat image, if I go from here, nothing is there. So only this part of the image is relevant to us for detecting the object, right? So it's very important. So whenever we use like a detection algorithm, we'll always end up having multiple boxes, right, in the or multiple windows in the image. It's up to us how we discard those windows. So Viola Jones does it using some cascade of classifiers. YOLO and those kind of algorithms, we have already seen that they use some sort of non-maximum suppression, right? So yeah, I mean this is what is given here, that using Jacquard score or using some intersection over union, which is basically the Jacquard score, we basically remove the redundant bounding boxes using this method called non-maximal suppression, right. So if given two bounding boxes, if we see that both the bounding boxes have a very high, very high intersection over union value, then we discard one of them, because only one of them is important. The other one is basically having a very high overlap with the previous one, right. So that is one method that is used to remove the redundant bounding boxes, along with this other method that we saw, right. There are other techniques as well which do not involve deep learning, right. They involve simple machine learning, and which are used to detect objects. One is this histogram of oriented gradients. So I hope that all of you remember that in SIFT we had gone through this, the histogram of oriented gradients, right. So that is why it's written here, that's a frequently used feature descriptor, right. So once you obtain the histogram of the oriented gradients from a certain image, you feed it to an SVM, and the SVM does a binary classification in the sense that whether there is an object or not, right. So this is again another very popular algorithm that I think came out in 2005 or something. So CVPR, I think. So yeah, I mean this is another algorithm which was used to detect objects using this particular feature that you are getting from the histogram of oriented gradients, and then feeding that to an SVM for doing this binary classification. Now we will come to the more modern method, which is bounding box regression for precise object location, right. So here, for example, yeah, so if we look at this cat, right, so here what we you can see that this bounding box, if we had made it a little bit smaller also, then we would have missed some part of the cat, right. But our bounding box could have been just like this, right. It could have been a little bit bigger than the already shown box. Could we say that that's a wrong box? No, right, because that already contains the cat. So suppose if we draw something like what I'm trying to draw now, so a bigger box. So even though we are drawing a bigger box, it's not wrong because it's still capturing the cat, but we do not want something like that. We always want the bounding boxes to be such that they are just, I mean the object is almost fitting into the box, right. So here what we want is, we do not want the model or the method or the algorithm to detect just any box around the object. It should just contain the object as much as possible, right. It should not contain, I mean anything extra, right. So that is what we want. So this bounding box regression method is added to those to the different algorithms, where we are also training the model. First of all, it has to predict which object the image belongs to. So for example, or the detected object, I mean what class it belongs to. For example, this is a car class, and I'll also learn how to put this box just around the car. So it shouldn't be a bigger box, or it shouldn't be like, I've just captured half of the car and I'm done, something like that. So that should not happen. I should precisely capture the object fully, but in such a way that I do not, my box doesn't include other unimportant things, right. So this method is called, so there are two tasks here. One is a classification task, where you are classifying exactly that if your suppose training set has 20 objects, right. So given a test object, you are classifying which object this particular image is belonging to. That is one thing. And second thing is that not only am I just classifying which object this is, I am also learning what are the precise coordinates for my bounding box. Okay, so so I don't know if it's visible or not. So basically for every corner we are predicting the maybe the length and the height and width of the rectangle and the like one of the corners of the bounding box, something like that. It doesn't matter what exactly we are detecting, but we are detecting 4 different values for a given box, right? So if we point out that this is the starting point, starting coordinate, and if we give the height and width, we can draw the rectangle fully, right? So this particular part basically, so this also we are learning. So this is a classification loss where we are learning the category of the object. This is a regression loss, right? So where we are exactly trying to learn where we should place the bounding box, right? So this is basically, you can say that this is the modern form of solving this problem. So either in localization or object detection, we use a similar setting. So if we want to come to just object localization for now, so just a reminder, going back here, that object localization is that the task is that you have been given an image. That image contains a single object and you are trying to localize it, you are trying to draw a bounding box around it, right? So an example algorithm is called overfit. So overfit actually was introduced like in 2013, and it was a winner of the challenge. So there was a challenge going on for 2 things. One is object detection and one is object localization. So bigger and better algorithms would win. Better algorithms who are able to detect the objects better, or who are able to localize the objects better, are basically supposed to win the challenge. So these things were very popular in the last decade, maybe not now. So this algorithm is a winner of the challenge, right? So what they do is, so first of all, they use so given an image, they do not use any handcrafted features anymore. So they pass this image to a CNN, it gets the feature maps, and then it basically learns how to it basically learns what is the category of the object through a classification task, and basically the regression loss to find the exact coordinates of the bounding box, right? So one thing that it does is that, so we have seen, right, fully connected networks. So they can be very they can be very resource exhaustive, right? So there can be, in a fully connected network, there can be millions and billions of weight parameters. So that is exactly why we came up with the CNNs. So that, because in the CNNs, with feature sharing throughout the image, the number of learnable parameters reduces drastically, right? So what they are saying is that instead of in overfit, instead of using fully connected layers, we completely replace the fully connected layers with convolution based computations. So something like this, right? So suppose this is an image, we are using a CNN, right? So maybe something like this, we have downsampled the image to this size, 4 cross 4 cross 256. We flatten it and we get something like some vector of this dimension, right? And then we keep on adding fully connected layers and so on with a lot of weights, etc. So this part is the problematic part, which has a lot of weights to learn, right? Instead, what we are going to do here is, we pass the image through the CNN. Then what we do is, this is the output size that we are getting. Then we are going to put another convolution, which will again maybe some pooling as well, so which will again downsample this. Then we will keep on adding some 1 cross 1 convolutions, right? And those 1 cross 1 convolutions we will keep on learning until we get a good vector, good feature vector for the image, post which we will add just a linear classifier and we will classify, right? So there are no basically in this part there is a FC layer like we have seen in traditional neural networks, and in this part there is no FC layer, we are just using convolutions in order to replace the fully connected layer, right? So this is what overfit used in the network. So we are not going into the details of the architecture, but we'll look at other algorithms in much more detail because they are more interesting. But yeah, this is one of the advantages of the overfit method, that they used instead of fully connected layers, they used CNN layers, which made the computations much faster, right? So now overfit is a technique, like I said, for object localization, right? So localization again means what? Just classify and localize, right? So the thing becomes much more challenging when you do object detection. Why? Because an object, when you are doing an object detection task, your image at hand can contain multiple objects, and that is where traditional algorithms do not do well. That is why we needed to come up with something more sophisticated, right? So in modern object detection, where there are multiple objects, so there are basically two types of detection algorithms. One is region proposal based. So here what we do is we use some algorithms. So given an image, suppose maybe if we go back here, yeah, so given an image like this, what we do is in the region proposal network, what we are trying to do is we are trying to find out the regions in the image that could probably contain an object, right? Different windows in the image we are trying to find out that can probably contain an object. So these, how to find out these potential regions in the image, so that can happen without deep learning, that can happen with deep learning. So we will see different methods that involve both, right? But the first step is always that we identify potential regions that could contain some object in the image. We do not know for sure whether they contain or not. Maybe there is some, there is some region in the image which has the same color, or some region in the image which has a similar texture, right? All those areas are grouped by some algorithm and they are given to you, and that algorithm, the output basically tells us that okay, this area in the image, they might contain important information about some objects, okay? So once these are identified either through deep learning or without deep learning using some image processing methods, we then take those specific identified regions and check those regions with a classifier. We try to classify whether there is an object in the region or not. If there is an object, we are trying to learn the detection boxes properly. So that is the region proposal based method, like the first method in object detection, and this is actually pretty good. Yeah, so this is actually pretty good, just that the problem is there are two stages involved. The first stage requires us to identify the potential regions, and the second stage requires us to classify and regress, right? So this two-stage approach can be pretty costly, and hence there is this second kind of method called the dense sampling based methods. So what this does is it clubs these two things into one shot. Okay, so it basically combines the two stages in this previous approach and combines it into one. It clubs the two stages into one single stage. So it integrates the region proposal and the detection into one stage, right? So the only problem with these two is that the first one, while it's pretty accurate, it takes a lot of time. The second one, while it is very fast, it may not be as accurate as the first one, right? So there is a trade-off always, and you can use whichever algorithm is more required for you only know what requirements you have. If you need something which requires very critical detection, then the second one, then the first approach would be good enough. And if you need something which has to be very fast, but you can allow a little bit of fall in accuracy, then the second approach would be more appropriate. So in a nutshell, what do we do in RCNN? So RCNN is the first maybe deep learning based famous model that came up, right? So what they do, so RCNN is one method that belongs to this first branch. So it has two stages, stage 1 and stage 2. In stage 1, like I said, that region proposals are obtained from an image. So using an algorithm called selective search, so we do not need to know what the selective search algorithm does, but just know this, that given an image, it will give you different windows in the image which are more probable to contain some object, right? So now given those windows, what we'll do is, now that we have the region proposals, that is the different windows, we are going to the second stage. Second stage involves what? That first of all, we'll in order to process all the images through a single CNN, we'll convert them to the same size, and then we'll take each of these region proposals, pass them through the CNN, learn to classify whether there is an object or not. If there is an object, then what is the object, right? And we'll also do a bounding box regression. So basically, if the suppose again going back to an example, so if your image said, suppose if your region proposal said something like this, maybe half a cat was marked as the region proposal, what we'll learn to do is, we'll try to put the window in the correct location by doing this regression, right? The regression is achieved by using an L2 loss, and the classification is achieved by doing by training it using a cross entropy loss, right? So this bounding box regression is also there, which is used to basically tell the model or teach the model that, okay, whatever region proposal was returned to me, that is not maybe the best bounding box or best window. We need to shift the window a little bit in order to capture the image in order to capture the object in a better way. So these are the two stages involved in RCNN. So that is not very difficult to understand. So only the stage 1 only gives us some approximate locations in the image that might contain images. In the second stage, you pass each of these approximate regions through a CNN, you classify what object is there, and then you learn how to put the bounding boxes in a better way, right? So this is RCNN, right? So this is kind of like the like a vanilla version, like a maybe a bigger version of the model, right? So this is an image, you pass it through selective search. Selective search now gives you different areas, right? They do not have to be of the same length also. So different areas of the image are returned to you, which are likely to contain some object. Okay, so to be very precise, the selective search algorithm, when operating on an image, it returns 2000 region proposals. Now what we do is, in order to be able to pass this through the rest of the network, we need to combine all of these region proposals into a similar size. So all of these are converted for the RCNN method, all of these are converted into 227 cross 227 images, right? Now each of these images that you got, they are passed to the CNN. A CNN like AlexNet or VGG, which is pre-trained on ImageNet as written here. So for each of these, you get different feature maps, and these feature maps are passed through an FC network, where there are three things that are going on. One branch is learning the class of the object. Second one, there's an SVM. So basically for each class, if there are 20 classes in the training set, there will be 20 SVMs, which will basically, using this FC network, it will basically tell you that whether a certain so it's something like this, that given the like the features from, taking the features from here, the class specific SVMs will tell you whether a certain class C is present in that image at all or not, right? Image means these warped regions, right? This subset of the original image. So each of these you are taking, and basically it's class specific SVM. What it will do is, it will take this image, convert it into feature maps, add a FC network, and basically it will say whether there's a dog or not, whether there's a cat or not, whether there's a television or not, things like that. And finally we have another FC layer, which is learning the bounding box regression. So this is trained by the cross entropy loss, this part is trained by the L2 loss, right? this is the entire RCNN method. So note that because this is older, people have still not given up SVM, so they are still trying to detect the algorithms through detect the objects through SVMs. But in the next algorithms, we will see that these parts have been eliminated, as this and this have been found to be enough to be able to detect objects, right. So a little bit more detail, that there are three training stages. One is softmax. So this is what, so basically we are trying to like fine tune. So this is an ImageNet pre-trained AlexNet, right. So if we want to, so this doesn't know, this pre-trained model hasn't seen this image at all. So in order to fine tune this softmax is present, right. So in order to fine tune the CNNs, right. So this softmax is trained by the cross entropy loss or the log loss, which is a alternate name for cross entropy. Then there is an SVM for each class, right. So basically one versus rest kind of SVM. So like I said, whether given this part, whether it contains a dog or a cat or a car or a television, etc., right. And obviously bounding box regression. So you will find this everywhere in all the algorithms from now on. So which is basically adjusting the correct bounding boxes, and it's trained by the L2 loss, right. So what is the main limitation of this algorithm? The main limitation is something like this, that each of these, so there are 2000 region proposals, we are warping them to the same size, and individually we are sending all of them to the CNN and we are doing the fine tuning, right. So that takes a lot of time. So training and test time are both very high, right. So that is a red flag for us, especially on the test time. We do not want the model to be spending too much time, right. So yeah, so then what we want to, so this was RCNN, this was the most primitive algorithm in the deep learning era that came up and involved some CNNs, right. So note one thing here, that there are these two, this softmax is there, this class specific SVM is there. So even though the softmax is performing some classification in order to fine tune this network, this entire network, the ultimate decision is being taken by the SVM itself, right. So it's basically like you are using the CNN features. So previously in the older methods you would use maybe something like okay, so maybe the right image is not here. So yeah, I mean, like we saw in Viola Jones, you are using hard like features here and you are using some classifier to classify, right. So here it's a little bit different. Here instead of using hard like features or fixed features, you are basically using a CNN which is learning the features on its own, right, and the ultimate decision is being taken by an SVM only. So this is like an older version, older model which was like created way before, I mean many years back, where people still use CNNs only as, you know, good features of a given image, but final decisions were still being taken by interpretable machine learning models like SVMs, right. So fast RCNN in that way. So what I said is that RCNN itself is pretty slow because of its two-stage approach, and because we are passing this each of these region proposals individually through the CNNs. So now people came up with this fast RCNN method. People means the same authors, I believe. So what they do is they use the selective search algorithm to get the 2000 region proposals. That's not a problem. But now they are saying that instead of passing each of these region proposals separately through a CNN, why don't I get the feature maps for this entire image first, and then I'll try to locate in the feature maps what this part of the image, which I mean where in this feature map this part of the image corresponds, where this part corresponds, and so on. That is easy to find, that is intuitive, that is mathematical, right. So the idea is that I'll pass this image only once through the CNN. I'll not pass each of these region proposals individually. Rather, I'll take the feature activation maps in the CNN and I'll try to I'll try to map where, if this part of the image, if it's located here in the original image, where will it be located in the feature map, right? So those have already been covered in the class, so we are not going through that, how this mapping is done. So it's a little bit mathematical and it's fine, right? And then you are doing some ROI pooling, etc., to extract out these regions, okay, of the feature map, and then you are doing the rest of the things as it is, right? You are sending you are sending the output here to the FC layer, where the FC layer has two tasks. So this time fast RCNN people did what? So they initially, it was like you take CNN features and feed it to a SVM. Here they are getting rid of the SVM completely. So they are having this classification head, and which is trained by the cross entropy loss, and the regression head, which is trained by a smoothed L1 loss instead of L2 loss, because it has been seen to be more stable, right? So these are the these are the different improvements that have been introduced by the fast RCNN people. And even though not in the slides, so we all have seen, or if you have gone through this week's lectures, so we have seen a plot which basically tells you like how much time RCNN takes versus how much time fast RCNN takes, and there is a remarkable change in the remarkable reduction in the test time based on this change in the fast RCNN, right? However, one thing that people still saw is that this selective search algorithm itself takes a huge amount of time for each image, which is undesirable, right? Hence this algorithm of faster RCNN came up, right? So here what we are saying is that, okay, now previously we were using a deterministic algorithm like selective search to take out the region proposals. Now why not we learn them? If we are learning so many things, why not learn that as well, right? So main addition of the faster RCNN is that this region proposal network, so you are learning the regions of interest using this region proposal network. You are no longer using the selective search, right? And how are you training this? So basically, if you have gone through the lectures, it involves 4 steps, right? The first, so each of those 4 steps are pretty involved, but they have been explained very clearly by sir, that you have this image and you have a CNN model which is used to train this particular region proposal network. So how is it trained? It basically it's trained to predict whether the regions that are the regions of interest that are output by this network, whether they contain any object or not, and what are the correct bounding box coordinates, right? So that is how this branch of the model is trained. Then in the second branch, you basically have a separate CNN and feature map, and you take the feature maps, etc., and you basically learn this part of the model. So basically the part that I am pointing out. So all of these are already taught by sir, so it's not, nobody should worry about these things. So they are very clearly mentioned in the lecture slides. I am just revising them with you. So you have the CNN, this entire branch is then trained, where the regions of interest are taken from this part. So this part is frozen in the second stage. In the third stage, what you do is, instead of having 2 different CNNs, you use a single shared CNN between these 2, right? And in the fourth stage, what you do is, you keep everything frozen here, right? And you only train the detector which will detect whether what class your each region of interest belongs to, and what is the bounding box regression, right? So this part, you will see that here the 2 things are very similar. The only difference is, here we are predicting whether there is an object or not. So this is a binary classification here. This classification, on the other hand, is multi-class, because here you are basically classifying that given your object of interest, what object are you, It's not just about saying whether there is an object or not. That's the only difference, right? So this is how this faster RCNN method works, and just eliminating the selective search algorithm here and converting it into this network, this learnable network, is actually seen to be very efficient, and the time taken is actually very less, which you can which is given here also. So one thing is to be noted that we have big models, very big models nowadays, and it's okay to take time to train them, right? But training time is fine, a lot of training time we are able to afford that, but test time should be very fast. That is always something that we should aim for, right? So if the test time itself is very big, it takes a lot of time to do some inference, etc. That is a very bad thing basically. So here you can see that RCNN for a single image used to take 49 seconds around to make a decision on the objects, right? There is another algorithm, SVPNet, which used to take 4.3. Then fast RCNN, in fast RCNN we basically removed the removed the criteria of having different CNN embeddings for all of these different regions of interest. So that reduced it to 2.3 seconds. And finally faster RCNN, by removing the selective search algorithm, it has been able to reduce the time to even lesser, to 0.2 seconds, right? So this in fact is still not very fast. I mean, it's pretty fast, but we still want something more sophisticated, right? So it's still, you can see that faster RCNN, if you go back to Sir's slides, you'll see there are 4 steps as is already marked here, right? So the basic stages are 2. One is to learn this region proposal network, and the other is to make the final classification. So this 2-stage network is what is costing us this much amount of time, right? So in later algorithms like YOLO came up, right? So YOLO, SSD, etc., these are all single shot algorithms. By single shot, what I mean is that it will club these 2 stages together. So region proposal and this part, they will be learned together, right? So one thing that is the got it. So one thing for like I said, so our YOLO is even used to this day, right? So we are probably only going to look at YOLO V1, but there's V2, V3, I think the most recent one is V8. So all of them basically add different functionalities to make the process faster, right? So so the question is, how does YOLO manage all this in a single shot? So what it does is, given an image, it divides the image into some S cross S grid. Okay, so like it's given here, it's a 7 cross 7 grid. The image has been divided into that, right? So now it basically learns the bounding boxes and the class probabilities together. Okay, and it basically does what? So okay, just a second. Okay, so given a certain grid cell, say the one that I am pointing here, it will try to draw different bounding boxes of different sizes, right, around this central pixel which I'm marking here, right? So at every cell location there will be multiple boxes, right? And that box is basically something that you can choose, number of boxes you can choose for yourself, right? And basically what you'll do here is, one thing is that you will try to predict whether this bounding, given this central pixel, this is not a pixel, this is the cell. So given this central cell, so given each of the bounding boxes around this central cell, so maybe somewhere around here, so given all the different bounding boxes around this cell, what is the probability of each of them containing an object, right? So it will just try to find out what is the confidence of the model. Rather I'll rephrase it. Basically, given this central grid and all the maybe some 20 bounding boxes around this particular grid cell, what is the confidence that, or what is the probability that each of those 20 bounding boxes, they contain an object, right? So that is one thing that the model calculates, and based on that, so these you can see some boxes are very deep colored and some are very lightly colored. So these scores are basically like the thickness of the lines, they are given by how confident, what is the probability that a certain bounding box contains an object, right? And also another thing that is predicted is that given this cell, what is the probability of the object that is contained here. One is that if we have 20 bounding boxes around the given cell, what is the confidence that each of those boxes contains an image. And secondly, separately, given this grid cell again, if it's part of an object, if there is an object around it or like inside it, what is the object, right? That is given by this class probability map, right? So if we suppose in this case, because this cell is basically this is part of a cycle, right? So here basically it should predict the cycle class, right? In this part it's only predicting if there is an object or not. In this part it's predicting the class, and both of these are happening together simultaneously, right? So divide the input image into S cross S grid. Each grid predicts B bounding boxes, so B can be anything. So in my example I am telling it to be 20, right? It predicts B bounding boxes and confidence scores for those boxes. So these confidence scores are learned. So these confidence scores basically represent like how likely is a certain bounding box to contain the object, right? It doesn't matter which object, just that how likely is it to contain a certain object, right? And finally, it also predicts conditional class probability per cell, per grid cell, right? So what is the probability that this particular cell is a dog? What is the probability that this is a cycle, car, etc., right? So that is what it predicts, right? So each of these bounding boxes have 5 coordinates, right? That the model has to predict basically. So just remember one thing, that it still uses a regression loss, right? So in order to make sure that the bounding boxes that are chosen, they are placed appropriately in the image, as appropriately as possible, right? So yeah, so what happens here is that for each of the bounding boxes detected, we have 5 things. One is the center coordinates, right? So if this is a bounding box, its center coordinate is somewhere here, right? I am talking about this one. Yeah, its center coordinate is somewhere here, right? And yeah, where were we? Yeah, the height and width and the confidence score, right? The confidence score is basically telling you that this particular bounding box, how likely is it to contain an object, and that is given by, the confidence is calculated in this way. It's basically probability that there is an object into this IOU of the ground truth versus the predicted. So by I hope all of us understand this, that in order to train these networks, we need to have so the training images have to be annotated with the objects, right? So we need a training image that will appropriately, that already has the ground truth bounding boxes. The model has to learn from there, right? So what it is saying here, that given a certain bounding box, right, whether, this is the probability that whether there is an object in that bounding box or not, and that I am multiplying with the intersection over union with respect to the ground truth bounding box and the predicted bounding box, right? So that multiplication, that product basically gives us a confidence score for each of the bounding boxes, right? And finally, we how do we calculate the class given that there is an object? So we calculate it in this way. So yeah, so we have this class probability map which gives, like, given this central cell, this cell that I was describing before, so it was predicting which class this cell belongs to, right? So now at test time what I will do is I will calculate this. I already have this probability from this part. Okay, so this probability, so you can see one thing, this is color coded. So each of these cells, you are basically, your model predicts that this part, this part, this part, this part, all of them contain this, right? They are in more vicinity of the car. This yellow part, they mostly contain the cycle part, right? And these blue cells, they contain the dog part, and so on, right? So yeah, so they contain the dog part. So you should go through this particular YOLO is not something that is simple to understand. So I would say that RCNN and faster RCNN are actually much more intuitive. So in this way, your class probability map converts this grid, right, S cross S grid, into different categories where each cell has its own class, right? So now at test time what you do is, so you find the, for a given class I, you find the probability from this probability map, right? You multiply that with the confidence, right? And this is what you get. So this this part basically says that probability of class I given object into probability of object, that becomes probability of class I into the IOU of the truth versus prediction. So that basically gives you what is the, whether based on the confidence score that you get here at test time, you will be able to understand how good is the, what object is there in a certain around a certain grid cell, right? Another thing that is not mentioned here is that in this way, it's already mentioned in the lecture notes, so it's fine, but yeah, in this way you can see, if you look at this image, right, so there are so many bounding boxes. Some of them we have colored with thick thick boundaries. So this one, the cycle one, the car one, so they are thick and they are fine. But does it look very pleasant if we have so many bounding boxes, like these light colored very light bounding boxes? They look unpleasant, right? So we need to make sure that we only retain the most important ones. And how we do that is through algorithm that we have already touched upon before, way before, which is this non-maximal suppression. So this is a key part in the YOLO algorithm, where it knows, it basically eliminates some of the overlapping windows. So suppose if I overlapping bounding boxes, so suppose this is the dog bounding box that I have detected, but suppose if I detected something very close, right, it would look unpleasant to have both. So I need to eliminate one based on how much overlap there is with the ground truth and how much overlap there is with another bounding box that has already been detected, right? So this is what the architecture looks like. So for us, the architecture maybe while it matters a lot, maybe how this YOLO model functions is more important. So this is not very trivial. So please go back and have a look at the lecture notes very thoroughly. And also YOLO is something that we generally look at, like the lecture notes obviously are there, but in order to fully grasp it, my suggestion would be to go to Google and look for, so there are innumerable number of blogs and resources available on the net. So you can go through the paper, you can go through the different versions, how they are different and so on, and you can maybe try and understand what is exactly going on here, because this thing itself is not very easy to comprehend, right? So there are some limitations in YOLO as well. So the recall is small, and there is a high amount of localization error. So note that here we were not using any anchor boxes. Okay, so these boxes were basically around a given cell, we were just drawing different sizes of boxes, right? So in V2 what they did was they introduced the concept of anchor boxes. So anchor boxes is actually pretty popular in faster RCNN. So again, going back, so this region proposal network, what it does is, inside what happens in this region proposal network is that you predetermine a set of anchor boxes, right? And those anchor boxes you are trying to fit into the image, and you are trying to see if inside those anchor boxes objects are present, right? A similar concept is there in this part, right, in YOLO V2. So they are introducing, instead of just haphazardly having different sizes of like bounding boxes, it basically generates anchor boxes, right? And there's a lot of nitty-gritty going into it, which you can go on and have a look at later. But yeah, I mean, it's good to have a knowledge of what are the faults with YOLO V1, such that YOLO V2 came up, then why YOLO V3 came up till like maybe the later versions. So all of them have different functionalities, right? So here, for example, so here, for example, there are a lot of learnings going on based on the anchor boxes. So you can go through them on your own time. But yeah, I mean, this was just to give you an idea that YOLO V, the different YOLOs, they basically, the different versions, they are trying to cover different scenarios, right? And obviously the current versions are obviously better than the older versions. So it's better to find out, read blogs and understand for your own sake, like which version does what and why are the new versions more important than the older versions. So you can go through the paper, you can try and understand exactly what is going on. So there are many other detection algorithms, like SSD is there, single shot object detector. So SSD is just like YOLO, which is just another algorithm which does these two things in single shot. And like I said, the problem with these two is that because it's single shot, its accuracy is compromised a little bit. There's low computation time, but accuracy is compromised. So what we want to reach is this high accuracy and low computation time, but there is always a trade-off. So the amount of time that you want to reduce, your accuracy goes down, right? So yeah, I'll maybe quickly move on to the coding part. So coding part, we do not really have too much in this week, but yeah, I'll just show you something and I'll share that with you right after the class. Yeah. So this is a collab notebook that we are having on object segmentation, right? Segmentation we have already, maybe not in the TA sessions, but in the class we have already gone through things like masked RCNN and so on. So this is a notebook meant for that. So this is basically CNNs for segmentation, right? So again, we are not going to go through fully all the details of the notebook, but this is just to give you an idea of how to create the different the unit architecture and so on. So we are already aware of the unit architecture now. So units, they do not only, so again, units, it's very important to understand them, because they are not only good for like object segmentation, instance segmentation, but they are also very useful for other tasks, including the more recent diffusion models, right? So it's very important that you go through this notebook and you understand units very well, so that you are able to contribute to the more recent architectures like diffusion models. So here the first cell, we can see it's all about, the first few cells are all about importing the different libraries, and there are some, you'll see some helper functions also present, which are plotting the different, which are basically different plot functions. So one thing is plot function, they are basically plotting the different plotting different things, And also because we are trying to, like you can see this function, so also because we are trying to generate, you know, different, we are trying to label the different pixels which are containing different objects, we want to mask, we want to create different colors for them, right? So all these helper functions are there in the beginning, right? The third block is basically about generating some random data with some shapes like triangles, circles and so on, right? So all these parts are not really very important to us, they are just some helper functions in order to just create some random data. Yeah, so they are present for, so that you can create some random data. So these are not really something that you need to go through very thoroughly, other than just like learning and understanding NumPy. So all of these have a lot of functionalities of NumPy, you can see, for example logical or you can see logical AND. So NumPy has a lot of functionalities which it takes years to understand them, right? So mgrid, so I want you to go ahead and look at these functions and try and understand what they are exactly doing, what are the functionalities that are present in these modules, right? So finally, after you generate the images, they look like this, okay? And yeah, so these are the generated images in black and white, and what you want is something like this, that your model should be able to generate these colors, right? So because there are objects here, right? So you want different colors for this different looking objects, that is what you want, right? So this part is the data set and data loader preparation. So the data set basically, yeah, it you can have a look at how this how this data set is created, right? So here you can see that in the transforms we have only used tensor and normalize. So this normalize is used based on like I said, the ImageNet mean and variance, right? And yeah, so here you basically initialize the data loader for the training and validation set, and finally this is the unit module. So this is something that you should go through on your own. So yeah, so you can see that from layer 0 to layer 4 we are going on downsampling. So here all the in comment all the details are given. So how you are, based on your first layer, your H and W are reducing, again further reduction until this is H by 32 and W by 32, right? And then you will start upsampling. So this is the point, yeah, this is the point, right? So then you start upsampling until you reach yeah, so until you reach the input. Hello, hello, I think I'll mute. Yeah, okay, right? So this is the entire unit model. So I'll share this code with you so that you can have a look at it on your own time, right? So this, you can see clearly how the upsampling and the downsampling are coded up. So this is how the model looks like. You start with the 0th layers and so on until you reach the bottommost part, and then you start upsampling them slowly, right? Then you go on upsampling until you have this output which is of the same size, same shape as the input, right? And then all you have to do is you have to instantiate the model first of all, and there are some details on the how the model looks like. So this is a basic unit, and other things you can try out, like printing the summary of the model and so on. So then you can define the dice loss and the final training loop, etc., So all of these are given here, and finally after your training they show that you have been able to recreate. So these are the, so basically these are the target, these are the ground truth labels for this particular data, right? So this is a test data after the training. So this is the original image, these are the ground truth labels for the individual objects, and these are the predicted ones, and you can see that they are pretty close, right? So I'll share this with you, and you can maybe like have your use your own images and try to generate. So obviously one problem with instance segmentation is that you have to annotate this entire training data. So all of these objects have to be annotated by yourself, right? So that itself is not very easy. So maybe you can try out some data sets like Pascal views, Pascal and so on. So all of these data sets are there already, and you can just try out this network and see what outputs you are getting, right? So just wanted to make you aware of this notebook, which is very useful for as it contains the entire code for master for like semantic segmentation. So yeah, I'll just share this with you. So fine, this is all I had for today. So let's then meet on Tuesday. So probably we'll talk about RNNs and the language, the text part in the next class. Yeah. So the notebook will be, I'll specifically share this one so that it's useful to you guys. Fine this then guys, we'll meet next week Tuesday. Thanks.